So welcome guys to the fourth event of the machine learning series of DSCode. I'm Pratyush, and along with me I have Rakshit to teach you logistic regression, cross-validation, and take you through the entire life cycle of a data science project along with the Titanic Dataset. So Rakshit, take it away.
Hi guys, I hope you all are fine. So today we'll be seeing about logistic regression and cross-validation. So what is logistic regression? If you recall, in linear regression, we used to determine the value of the continuous dependent variable. Logistic regression is generally used for classification purpose. Unlike linear regression, the dependent variable can take a limited number of values. That is, the dependent variable is categorical. So for example, for logistic regression, it's more like you have a cancer or you don't have cancer, pregnant, not pregnant, or like classifying digits, 1, 2, 3, 4, 5, 6, 7, 8, 9. But for linear regression, we were seeing like continuous data sets like house pricing or iris data set. Those were continuous data sets. So in logistic regression, we used to take the weighted sum of inputs. But in logistic regression, we can't do this because the value for logistic regression should be between 0 and 1. So we pass the summation into an activation function known as, for the logistic regression, it's the sigmoid function. So for the sigmoid function, the value can always lie between 0 and 1. So we can see that this is h of x is equal to 1 by 1 plus e power minus theta transpose x is called as the sigmoid function. So sigmoid function is greater than 0.5 if theta transpose multiplied by x is greater than 0 and theta transpose multiplied by x is less than 0. So we can see that for a sigmoid function, if it's greater than 0.5, we consider that it is belonging to that category, and if it's less than 0.5, we consider it not belonging to that category. And so, for example, we have a data set, and we scatter those data sets, and we can see that the admitted data come on one side of the graph and the others on the other side of the graph. So when we draw a decision boundary, which we'll get using the logistic regression, so we get value parameters for the logistic regression, and with that we'll be drawing the decision boundary. So when we draw the decision boundary, any value when we test it, which comes behind that side of the decision boundary will become admitted, and this side of decision boundary will become not admitted. So today we are gonna, for the coding part, we'll be using a data set which consists of marks for out of 100, which consists marks for 2 exams for 100 applicants. So the target value is either 1 or 0. 1 which represents admitted and 0 which represents not admitted. So decision boundary is not necessarily needed to be linear. Decision boundary can be non-linear as well. So for example, this is an example for non-linear decision boundary. So we can see that the decision boundary goes somewhat like this as a curve. So decision boundary is necessarily not needed to be linear. So this is known as the confusion matrix. So what we can get from the confusion matrix is that we can know the how good the model is working. So for example, we have the actual values, and then we have the predicted values using the model. So when both are positive, so when the actual value is also, for example, in our data set, when the actual value is admitted and the predicted value is also admitted, then it's known as true positive. But what happens when the actual value is negative, but the model predicts it as positive? The model predicts as not admitted, and the actual value is admitted. So then it's known as false positive. And when the actual value is positive and the predicted value is negative, it's known as false negative. And when both the actual value is negative as well as the predicted value is negative, it's known as true negative. So for example, when you see a man and a doctor tells him that he's pregnant, so that's an example for false positive. As you know, a man can never be pregnant. And in this picture, it's so obvious that the woman is pregnant, but the doctor says she's not pregnant. So that's an example for false negative. And now we'll be seeing about cross-validation. So until now, we've been splitting the data into, before that, do you guys have any doubts regarding logistic regression? Feel free to open up a chat. So all good?
Yeah, all good.
Yeah, okay. So let's continue with cross-validation. So until now, we've been splitting data into training and testing data. But for real data scientists, they will be splitting data into training, validation, and testing data sets. So why do we need validation data sets? So at times, the model will overfit or underfit the training data set, and it's not necessarily, it is not necessary that it should work properly on the testing data set. So we need a validation data set so that we make sure the training data, the model is perfect. It suits each and every kind of values present in the data set so that it works really good on a testing data set and works really good in a real life. So what and why is cross-validation? In cross-validation, we run a modeling process on different subsets of the data to get multiple measures of model quality. So for example, if you have a small data set, we split the data set into, like we have a data set of 500 items. We split into 100 each, and we run each and every time. So we need to run as training data set the first 400 and the next 100 as cross-validation. And the next time we run the second 400 as training data set and the first 100 as cross-validation. So cross-validation gives a more accurate measure of the model quality, which is very important when you're making modeling decisions. So this means shows that never choose the testing data set to choose the model. We have cross-validation for that. So whenever we are choosing a model, we need to check if it's properly working on a cross-validation and not on the testing data set, because cross-validation gives you the perfect accuracy, and we would know that if it would really work in real life. So let's get into coding. So first, probably let's name a Jupyter notebook. And then first, we need to import the necessary model libraries. So let's add a markdown cell. So NumPy, basic stuff, that's NumPy, pandas, then matplotlib, pyplot as PLT, then from sklearn.linear model, let's import logistic regression.
Rakshit, can you make it a bit bigger? That's okay.
Yeah, sure. Just give me a second. Is it okay? Is it good now?
Abratim, is that better, or do you want it more? Yep, perfect.
Yeah. So logistic regression, and then find test split, sklearn.model_selection. Then from sklearn.metrics, let's import accuracy score.
Rakshit, your model selection spelling is wrong. There's typo there.
Yeah, thank you. And confusion matrix. And matplotlib inline. So that when we save the Jupyter notebook, we save it with the graph. So next, let's add a markdown cell saying getting the data. So let's get the data using read_csv of marks.txt. Let's just give it a second for it to complete its run. Have you guys loaded the data? Is it good? So let's see how data is. So this is the data. Are you guys getting the data as well?
Probably did. We'll just take silence as yes.
Okay.
Yeah.
So let's get the X values from the data. So data or hierarchy of so let's check for X dot add first few values. So these are the first few values, and X dot shape. So it's 99 values, and then let's get Y values. Data dot hierarchy of -1. Let's check Y dot head. So this is Y dot head, and then let's get the admitted and not admitted separately. So admitted is equal to data dot hierarchy of Y equal to 1. Oh, sorry, typo. And not admitted is equal to data dot LFC of Y equal to 0. So let's check the number of applicants who have been admitted and not admitted. Admitted dot shape. 60 people have got admitted. So I guess 39 people have been not admitted. Let's check it out. Yep, 39 people have been admitted. So let's see it in a graph. plt.scatter. Admitted the LOC, the ILR of admitted the ILR of and then plt.scatter not admitted. Zero, then not admitted again. However, then now let's
Hey Rakshit, I had a doubt.
yeah.
So can I just scroll up? Actually, no.
Yes.
Can I just scroll up? So for your when you're ilocking the X for the X row, like data.ilog, why have you put a -1 there? Like, why can't it just be a colon?
Okay, so I put a -1 so that I wouldn't get the last row, I mean the last column.
Why not?
Because X is just the attribute and this is the target variable. So I just need X. I just need the attributes into X. So I wouldn't be including my last row. So the last row would come under the target value. So target value is Y.
I see. Okay. Makes sense.
Yeah. Okay, and let's show it. So this is the graph, but I don't understand what the graph is. So let's design it much better. So let's make the sizes. I guess the size is good. So just let's label it. Label equal to admitted. Label equal to not admitted. And let's put the X and X label and Y label as well. First exam. And the Y label is marks in second exam. And let's open the legend as well. So yeah, so we can see that the decision boundary should be approximately something like this, so that the admitted goes on top and the not admitted comes below. Okay, so let's train the model. So before that, let's split the model as well. So for that, let's do a markdown cell, splitting the data. So x underscore train, x underscore test, y underscore train, y underscore test is equal to train test. Yeah. Train to split of x comma y comma test size is equal to 0.33 comma random underscore state is equal to 42. So make sure you guys set random underscore state is equal to 42, because so that me and you would be getting the same testing and training data set. So let's run it. And now let's do another markdown cell saying training the model. So model, let's initialize it. So logistic regression. Now let's set the model.get of x underscore train, y underscore train. So we can see that the model has been fitted. Let's predict the values for the testing data set. So model dot predict x underscore test. So let's check out the accuracy. Accuracy underscore score y underscore test and predicted. Okay. Ooh, we can see that it's an 82% accuracy. That's pretty good that's pretty good. And let's see about the confusion matrix so that we can know how many true positives and how many true negatives we've got. So we could see that there are 12 true positives and 15 true negatives. We can see that there are 6 which have been selected incorrectly. So we have 3 true false positives and 3 false negatives. So that's it. Now Pratyush will be carrying on with the Titanic Dataset. Pratyush, you can carry
on. Thanks, Rakshit. So with that, we just finished logistic regression and cross-validation. Now we'll be going into a lot more interesting stuff, I'd say, throughout this entire series, which is taking you through the entire life cycle of downloading your data set, cleaning it, using a predictive model, and pushing it through and finding its accuracy, right? We'll be going from start to finish throughout the entire thing, and I'll take you through this journey. So first and foremost would be to download the data set, right? Awesome. So we're going to be working with something called the Titanic Dataset. So the Titanic Dataset is essentially the holy grail for data scientists. So it's the first thing that any data scientist really steps into. To download the Titanic Dataset, we go through something called Kaggle. Now, Kaggle is an online data science forum or community, which is simply kaggle.com. Wow, that's enough. And on kaggle.com, you have essentially millions of data sets, hundreds and thousands of competition. And it's a hub where data science data scientists themselves come together and share insights, stories, and discussions on any possible data set that could be helpful for the world. As you can see, there's COVID-19 data sets, there's data sets on corporate frameworks, there's notebooks on very complex deep learning models to even the most simplest machine learning models, right? So once you go to Kaggle.com, you simply search for Titanic. And I want you guys to do this with me because I will take you through the entire step. You'll have to use this particular data set to do our analysis, right? And so you search for Titanic, click on the Titanic dataset or the competition. And as you can see, this is the overview of this Titanic competition, right? Now, a little backstory behind why we're choosing. There is no particular reason why we're choosing this, really. It's only because it's a small but relatively easy to understand data set that really gets people going. A little backstory behind the Titanic, for those of you who don't know, is that the Titanic was one of the biggest vessels of its era, 1910 to 1912. It set sail from the UK to New York on April 15th of 1912. And unfortunately, due to seasonal icebergs, it crashed into one, and about 1,500 people died out of 2224. The Titanic at that time was deemed unsinkable. It was one of the biggest ships and one of the strongest ships that ever been made. And it was in writing that this ship could not have been possibly sunk until this disaster happened. So what we're going to do is we're going to build a predictive model based on the data that we have is data of every single passenger that was on the Titanic. So we will have things like whether they survived or not, the passenger class, the sex, male, female, age in years, sibling, spouse, so the number of siblings or spouses that particular passenger had, the number of parents or children that particular passenger had, their ticket number, fare, or how much they paid, their cabin number, and where they embarked from. So the Titanic took off from 3 ports in the UK and moved all the way to New York, right? So the 3 ports are Cherbourg, Queenstown, and Southampton, right? So in passenger class, you have only 3 variables, first, second, and third, to denote upper, middle, or lower class. Age, pretty self-explanatory. Siblings, spouses, and parents, children are just numbers, right? So I would scroll all the way to the bottom and download all, right? So I would download all my data, of course, open it up to see what it's like. And once I do that, actually, let's just open this in the Jupyter Hub notebook itself. So for you guys, since I've done this before, rather, let's just go through the entire thing anyway. Unzip it, move the data, just the entire load of it. So I'm going to take this. We don't need the gender submission as of yet, just the train and test.csv. I'm going to have to look for my Jupyter Hub file. All right, I already have it, but there you go. I've basically almost done the same thing, which is take those data sets, put it where my Jupyter notebooks are. And so now if I want to access my Jupyter notebooks, there it is, my train.csv and test.csv, right? So just like that, I'm going to open a new notebook so we can start this entire analysis together. So with that, we start with the very basics, which is importing our libraries, right? So I'm just going to increase font here. Hopefully it's much better now. Import and as a PD, import numpy, import seaborn, import map.lib, Python is PLC, and the standard matplotlib inline for Jupyter. So once that's done, we will import our datasets. So simply put, we do train is equal to p dot read CSV. P dot read CSV again, and I want to read the test file. Also, guys, if in any case I'm going too fast or too slow and you don't understand anything, feel free to talk over me. I'll post it in the chat. I'll be more than happy to explain whatever I'm doing. Right? So once I have that, as always, first thing you do is train.head and a test.head, because you want to understand what your data is actually trying to tell you. And if you do a .head essentially returns the first 5 variables in that particular data set. Sorry, the first 5 rows in that particular data set, right? So the first 5 rows, of course, are very generalized, really tells you what's there, what's not there, based on your columns and based on certain types of data. As you can see, I have passenger ID, just going from 1 to how many ever passengers there are. It's as good as the index. Survive, this is my target variable. This is what I'll be trying to predict and train towards. The passenger class, 1, 2, 3, first, second, and third, or upper, middle, lower class. I have the name of the passenger. I have their sex, male, female. I have their age in floating point variables from maybe 20 to at a max 100 or 110. Siblings, spouses, parents, children, they're just numbers in the end, possibly helpful. Tickets or ticket numbers, quite complex, not sure what the data is really going to tell me. The amount they paid for that particular journey, cabin, and as you can see here, we have some special null values, right, which we will tackle with soon enough. This, as I said, this is as good as what you get in real life data. Not as good really, but something similar to real life data. So we'll be trying to go through the entire course this way, where we clean null values, we substituted with some good correlative events, and essentially the full package. And with that, we have embarked as well, where you have S for Southampton, C for Charlottesville, and Q for Queenstown. Awesome. So looks like we know what our data set is or how it looks like. And even our test is about the same, where a passenger ID just starts from 892. So you could assume that your train goes from 1 to 891, and your passenger ID is 892 to so forth. And this is about the similar, except I see a lot of null values. So with that, I'd really like to know how many null values are there and how well I should really clean this data, right? And so I start off with sns.heatmap train.isNull. So before that, I'm just going to show you what train.isNull actually does, right? So I'll just do plus train.isNull. So as you can see, what train.isNull is doing is that it is returning false for every value that is not null and true for every value that is null, right? It returns an entire data frame with false and or Boolean values. So if I put that through a heat map, I'm going to get this beautiful map that tells me where it's null and where it's not. It doesn't give me the number. I don't really need the number. All I'm trying to look for is how much of it there is and how bothered I need to be with this particular data set. And as you can see, my cabin is almost empty. So for most passengers, I don't really have information on the cabin column. And for the age, there are quite a few that are null, but I think we can change this, or we can replace this with some useful information. Similarly, if we do sns.heatmap test.isNull, see what our test.csv looks like. It's about the same. So your cabin is almost empty. Age is slightly empty, but we could replace it with some useful information. So what I'm going to do first is that I'm going to drop the cabin column, because there are so many values It makes no sense to replace it with anything useful because there are no useful values to use in this case, right? And so to drop it, I just do train.drop the column, which is cabin, axis equal to 1 because I'm dropping columns. If your axis is 0, you're dropping rows, and in place equals to true. And what that does is that it actually solidifies to say that, okay, this cabin will be dropped permanently from train. If you don't specify in place equals to true, then what happens is that it returns the data. It returns a data set which has dropped the cabin, but it hasn't happened in the real data set as itself, because Pandas tries to save as much information as possible to avoid information loss or any mistakes, right? So once I do that, if I do a train.head again, as you can see, I don't have any cabin anymore. This is what it is, right? And anything I do to my training data set, I do to my test. So again, cabin, axis equal to 1, in place equal to true. And the same thing has happened for the test. Awesome. So we've dropped our first column, which was practically useless. Now we need to know what to do with the age column, right? Because there are quite a few missing values, but I'm pretty sure we can replace it with something meaningful. Because why we're trying to do that and not just drop the column by itself is only because there could be some useful information where there is data, right? If there's more than 50 to 60% of data, you can consider that column to be useful because it might have some correlation to the end target variable. So what we want to do is replace it with some meaningful data, right? And with that, we need to find correlation, if there is any, between any of these columns. So that is essentially featured engineering. You're trying to construct new features based on your existing features or your existing data set. So what I'm going to do is I'm going to create a heat map again because visuals are the best. Heat map train.core. The train.core is essentially a correlation. It returns the correlation between every single column. So if I plot a heat map for it, as you can see, it goes probably from -6 to all the way to 1. My passenger to passenger ID is always 1 because the column to itself is highly correlated. And there are certain columns over here, like passenger class to fare, which is almost -0.6, which is a really good indicator of, which is to say that fare and passenger class are very highly negatively correlated, right? You have certain correlations like this that are slightly negatively correlated, slightly positive, sibling spouse and parent children, and the survived column is slightly correlated with the fare, right? So sort of useful, not really that interesting, but I think we can. So we're looking for age, right? And we want to see what's a good correlation with age. So far, the best correlation seems like it is fare, because our passenger ID isn't really a correlative feature because it's just the index. It's just going to give me false values if it actually shows some correlation. But fare seems to be slightly correlated. And so what I'm going to do is I'm going to visualize it even further with a box plot, right? To do that, I do SNS.boxplot, x equals fare, y equals age, and data equals train. Taking quite a while. I think I swapped x and y by accident. So on second thought over here, of course, oh wow, all right, makes no sense. how about we change this to P class? And the reason I'm changing it to P class is because as I was looking at this entire heat map, so age is slightly positively correlated, about 0.1 or 0.2, but something like P class was closer to like slightly more negatively correlated. So the strength was a little more than what I'd expect. And so as I plotted P class, I see that first class ranges anywhere between 0 to 80, which is bad for me because I'm trying to find some specific value. And remember, in a box plot, the smaller, so remember, your box plot, the bottom line is your 25th quartile, and your top line is your 75th quartile, right? So that is essentially to say that most of your data lies within the box. So the thinner your box is, the better it is for you, because it's showing that a lot of people are in that particular box or in that particular range. So that range is highly indicative of something rather than all the data being spread out to nowhere, right? And so my first class lies anywhere between 27 to 50, where my mean is around 37. And that's only because I've noted the mean down. But right, so this is about 37. My mean here is about 29 for second class, and for third class is about 24. And second and third class are slightly better because their values don't extend so far. They have a couple of outliers, but that's okay because most of this is lying between your exterior lines and within the box as well, right? And so I think this would be a good correlative factor for my age. And so what I'm going to do is I'm going to define a function that I could use to help apply the age to every single row in my data set, right? And so what I'm going to do is I'm going to define a function, apply age, that takes columns. And by columns, I mean the data frames columns. One sec. Just going to get this code out because I wrote it just before. Don't want to forget. Right. So my age column would be maybe my 0th column from this. And my passenger class column would be first column in this. Now, if it's not making any sense right now, the function that I'm writing, completely fine. Just give me probably 2 or 3 minutes. And as you see it happen in action, you'll really understand what is going on. But until then, just follow through if you can. So if pd dot, oops. So if that particular column is actually null, then I'm going to get a class again, right? So p class 1, I'm going to return the mean value of 37. Lf class 2, I'm going to return the second class's mean value, which is 29. Else, I'm going to return 24. And if it is not null, so if the age is what it is, I'm going to return the age itself. Right. Awesome. So again, I'm just going to go through this function so you guys get a better understanding of it. I'm going to pass in 2 columns, which is my my age column of the data frame and my passenger class column. I'm going to check if the age is actually null. If it is null and if the passenger class is 1, which is to say first class, I'm going to return 37, which was the mean age of that particular class. If it's second class, I'm going to return 29, and if it's third class, I'm going to return 24. And in case that column was not null, I'd like to preserve the data and therefore return the age itself. Right? Now, how do we actually put this into our data frame? We will use something special called.
Brad.
Yeah.
Hey man, we have a question over here.
Oh,
yeah. So Nicholas asked, parameter is called and the function variable is called. Oh,
thanks, Nicholas.
it's
thanks.
typo. Yeah.
Yep. Awesome. So with that, we're going to use a special function, which is the dot apply function in a data frame. Now, the dot apply function, I will just show you in a bit. So as I said, I'm passing 2 columns to this particular function, and I'm applying apply age. Equal to 1. So what this particular column or what this particular line of code is doing is that it's sending in 2 values, which is the age column and the passenger class column, and it's applying that particular function, which is apply age, to every single row of that column, and in turn returns a new row which we will assign to the age column itself, right? And the axis again is 1 because I want it to go down the data frame. So if I run before this, I'm going to show you what happens before and after. So n.age, as you can see, my last bit, probably 888, is an NaN value. Rest of it is all fine, 22, 38, 26. Now, if I run this, and if I output it again, as you can see, 888, 24. So we could definitely say that was a third class row, right? And again, all the value that was there is preserved, and the new value is just put in. And if I were to do estimates.heatmap, train.is null, so I want to check the null values again. Looks fine. I don't see any null values, so we've potentially fixed that, right? And again, whatever we do for the train, we do for the test. So again, test age, and I'm going to pass in the same columns because it's the same for the train and the test, right? And with that, I'm pretty sure it's going to be null, right? Now, going back to our data set, what else is there that we need to do that we haven't done? So there's some gibberish here, which is your name. We're not using natural language processing, so we can't really take much from the name. There might have been some royals or some highnesses that would have been saved, and I'm sure that would be really helpful to us, but we aren't dwelling into NLP yet, so we'll set that aside. Same for the ticket. So we will drop the ticket, and we will drop name, and we will drop passenger ID, because in the end, it's just an index, and it's nothing correlative or nothing useful to predict our data, right? So again, I'm just going to do train.drop passenger ID. I'm going to drop name, and I'm going to drop my ticket. Plus axis equal to 1, and in place equal to true, right? Oops. What's the issue? Oh, my bad. My bad again. Awesome. So if I just do a train ahead, as you can see, it's a lot more cleaner with all this gibberish set apart, right? And we have only the useful data left. So even for the test, we need to clean our passenger ID, our name, and then our ticket. So what we're going to do is copy this entire thing, paste it. I'm going to replace that word with test because it's essentially the same columns. And test.head should look much cleaner. Right, so there we have it. A much cleaner and much more useful data set in the end. Now, as you can see here, we are going to do one more feature engineering or one more cleaning tool. So if you can see, embarked has Q, S, and C. Essentially three, how do I put this? Categories, right? Three letters that denote something. And even for, even for sex, we have male, female, again, 2 words to denote that category. What I'm going to do is I'm just going to convert them into numbers, right? Because it's much more easier for the model to interpret it as well. Like for sex, male, female could be 0, 1. For embarked, we could have the 3 destinations of 0, 1, 2. Or for each destination, we could have a column where it's 0 for that particular column. If the destination is not, like for example, QCS, if it was Q, then for the Q column will be 1, for the CNS column will be 0 and 0, right? So I'm just going to convert them into numericals for the model to understand it better. And if we do convert it into numericals, we won't just have to pass it into our logistic regression model, which we will use in the end, but we can pass it into various others like KNN, for example, the one that you learned in week 2, right? So what we're going to do here is we're going to again use a special function called pd.getDummies. And to know what getDummy does, I will return, I will output the particular value to show you what's actually happening. So getDummies text. Right. As you can see here, female 0, male 1 for every male female row there is to it, right? If my first 5 rows are male, female, male, male, female. So for males it's 1, for females it should be 1 in the female column, 0 in the male column. Pretty self-explanatory, but a very useful function if you want to convert categorical data into numerical variables. Now over here, what I'm going to do is I'm going to use another argument called drop first. And what drop first does is that it drops the first column it has. And that's only because male itself is predictive of what it's doing, right? If it's not male, it's possibly female, right? So in this case, in these 2 columns, it's unnecessary to have another column because the first column itself is self-explanatory to the model as well, not just to us. So if I do a drop first, I have only 1 column, and that's really all I need in the end. So I'm going to do this for the text variable, and I'm going to do this for the embarked variable, right? Because I want values even in that. All right, before this, I will just store this so I can output what embarked also shows us. Drop first. Oh, let's not drop first. So as you can see, for 3 variables, it's 0 for the other 2 and 1 for the third variable, right? And even in this case, what we could do is we could drop the first column, because every time it's C, it's guaranteed that Q and S will always be 0, and the model can interpret that as well, right? It's unnecessary to have another column of data because it's just computationally inefficient and takes a lot of time. So even in this case, if I do a drop first equal to true, it returns Q and S again, and every time it's 0, 0, we know it's a C, or we know it's the ship is embarked from C. And again, I'm going to store this in my embarked variable so I can concatenate it with my data frame later. And all I have to do is p.concat. p.concat train text embark, and of course axis equal to 1. It will return whatever I just got, right? So I have my male column, I have my Q and S column from the embarked, and there I go. I'm going to store this as my new train variable. And of course, so now that I've done this, I can drop the embarked column and I can drop the sex column because I already have that information with me. So I do a train drop sex embark. equal to 1, in place equal to 2. No, embarked. So, as you can see, right now it's the cleanest it could possibly be. This data set, I have all the information that I absolutely require, and the rest of it, I've thrown it out or modified it. Again, what we do for the train, we do for the test. So I'm just going to copy these two, because thankfully it's just changing the word train to test. Test, test. All right, sorry, I don't want to lose data, so I'll just store this in another variable name. And once that's done, I will concatenate it. Test, this the test, and then I want the test production. And now if I just want to see my test variable, of course, plot. We just need to drop the sex column and the embarked column. With that again, I can copy this, paste it here, change train to test, and test.head. There you go. Much cleaner. I'm just so happy when I see this data because I've cleaned it. It looks really good so far, and it suits whatever I'm going to do right now. Right. So with that, we have finished all our cleaning essentially. With the toughest part of a data scientist's job is actually to clean, understand, and feature engineer the data. So once that's done, we are going to do some final checks to see if we have in fact got all the null values. So I'm just going to do a train.isNull any, right? And I have false for everything, which is a good indication for me. And a test.isNull, again, check all variables. Okay, so it seems like we still have some null values, and it's quite odd, right? Because it didn't show up in the heat map. So what I'm going to do is I'm going to fetch all the data that is actually null, right? Test, right? Test.isNull. Oh, my bad. Oh, blocking the key. So, yeah, sorry. Since only the fair column is actually null, I will look for all those values where the fair column is null. And as you can see, there is only one value in the row, which is in fact null, right? And it's the fair over here for column number 152. Again, what we do is the standard procedure that we have learned over here. Again, note that this procedure is not really, it's not essentially the standard procedure for every single data science problem, but just for this particular data set and just to make things easier. We're going to visualize it with a heat map. So we do, actually, we're basing everything on our training data. So we use train.core. Once that's done, we are looking for a good indication for fair. And as you can see, straight off the bat, passenger class is a really good indication for fair. It's highly negatively correlated, about negative 0.6 as compared to the rest, right? Which lie between 0 to 0.3. So that's a really good indication for me. So once I do that, I'm again going to get a box plot where my X is passenger class, Y is my fare, and my data is train. This again is a very good indication because, like I said, the thinner your boxes are, the more your data is squeezed into that particular box, which is to show that that data actually means something as compared to your box spread out and your data is almost everywhere, right? The strength of this data is very, very high as long as the box is squeezed. So with that, what we are looking at is my passenger class is 3. And in my passenger class, which is 3, wow, fantastic. So it's the thinnest in my third box, right? And so I'm just going to look for the mean value because I can't really understand it. It just shows me the strength of my data, right? And so I do a train. Right now, I'm just trying to find that particular value, which is predicted in that box. So I'm going to call the column predix3, and I'm going to call that particular fair column, and I'm going to find that mean. Now, don't worry, we'll break this down step by step, right? So just understand that the mean over here for the third column, or sorry, the passenger class is 13.67. What I did right now is I started off by gathering all the rows where the passenger class is in fact equal to 3. So it returns me it returns my data set, but only those rows where the passenger class is actually equal to 3. So as you can see here, we're missing some columns, which is fine because I wanted only those columns where the passenger class is in fact 3. So with this new data set, I want only the fair column. And so I call fair. And so I have that particular column. And in this entire fair column, I just want the mean, right? So I can actually apply it to my 152nd row over here. And so I do a dot mean, and that's exactly what I get. Again, your first steps should be to split everything as much as possible, really trying to understand what you want to do with the data. And as you get better and better, it often comes down to one-liners, which are really helpful for you to read and understand the data, right? So I have 13.67, right? I'm just going to set it as 13.7 for that particular column. So test.log 152 fair, right? Let's just see. It's a non-value, fantastic. I'm going to assign it a value of 13.7. And now when I output this again, hopefully it turns back 13.7. Amazing. So with that, we will check once again if the test actually has any null values. And we find that it does not. So we finished our entire cleanup and on to the spicy stuff of data science, which is like training the model, testing the model. Now this is just maybe a 2 to 5 minute job, but the rest of it, I've actually taken you through whatever a data scientist does, which is check for null values, check for those values that are correlative, do some feature engineering, clean it up a bit more, and finally present it. Have it ready for you to train it to any model. Now again, choosing a model itself is also a skill, but cleaning your data is even more of a skill and even more valuable to the data science community or to what you're doing as a project. So to start off with my model selection, I would import, from sklearn. Sklearn.model selection, import test split. From sklearn dot linear model, import logistic regression. And then from sklearn.metrics, because we actually want to learn how well our model is doing, import classification or report. Again, a new metric. I will explain what it does, and the confusion matrix. Awesome. So with that, What have I spelled wrong? Cannot import classification report. Classification report. Right, how have I spelled it wrong? Oh, there. Awesome. So with that, I want my X variable, which is train everything except my survived column, right? Because my survived is my target variable. As you see here, or no, here, right? Everything else, survived is my target variable. So I'm going to drop survive and it's going to return a column. So it's going to return the entire data frame without the survived column. So my X will be train.drop survived access equal to 1. Then my Y variable would be train survived. Right. And so with that, the X train, the standard train test split lines, which is X train comma X test, Y train comma Y test. Train test split. I just use a tab to autocomplete. Makes my life so much more easier. Hope you guys are using the same IDE. And my test size. Now again, another feature of a data scientist is to know what test size to use, right? It's data science is essentially building an entire photo out of just a couple of jigsaw puzzle pieces, right? And you need to choose the right piece every single time. So the reason I'm using 0.2 over here is because I have only 600 records and I'm trying to maximize my training as much as possible so I can actually predict something in my test data, right? I already have a test.csv, but even my training, even in my training, I need to know whether it's actually performing or not, because my test.csv does not have any survived column to predict whether my accuracy was good or not. So in my train.csv, I'm going to split it into my training and testing, and then I'm going to predict it on the testing.csv. So again, like I said, I'm using 0.2 only because I'm trying to maximize my training data as much as possible. Best practice is to use anywhere between 0.2 to 0.33, right? And I'm trying to choose the lowest. So once I do that, I have my training test. I'm going to call my model, which is a logistic regression model. I'm going to fit my data, which is X train, Y train, and then I'm going to log predictions, log model predict X test. Awesome. So you can ignore any warnings. As you can see, the 3 standard steps is calling a model, fitting it with train or your X train, Y train, which is actually training the data, and then getting predictions out of it. So you want some predictions for your X test, and you actually compare it with the real values, which is Y test. So again, like I said, we imported classification matrix and the confusion matrix. Sorry, classification report and the confusion matrix, and we will see it in action. So I'm going to print the confusion matrix, which is my predictions, my Y test. And there you go. So the top left is my true positives, and the bottom right is my false negatives, right? And it's doing quite well. So 92 and 51 as compared to 22 and 14. So these are the values. The 22 should have gone to the left, 14 should have gone to the right. That was the misinterpreted values. But I'd say so far my model is doing quite all right, right? And if I want to know how much the accuracy actually is, I do a print classification. I'm just going to tab my predictions, which is log pred, and Y test. So in this, I see some very useful information. And so it's precision, recall, F1 score. So my precision, which is, so as you can see in this confusion matrix, my top left is true positives, my top right is true negatives, my bottom left is false positives, and my bottom right is false negatives. Now, why is that important? Because this is what precision is trying to do, right? Your precision is essentially your total predicted positive. So it's actually taking the true positive values divided by true positive by plus false positive, right? And it's giving you your score in the end, or your percentage. So my precision for all the false values, for all those that have not survived, is 87%. So positively, it's doing very well. But to say that it's actually getting the positive values just fine, 87%, that's actually pretty good, right? And even to predict all those who survived, it's getting all the true positives just fine, around 70%, which is still okay. Possibly because there wasn't much of the, there wasn't much of those who survived, right? So even in our data, it would reflect that. And so there isn't much training data even for those who survived. So 87% and 70%, really good. And then our recall is true positive and false negatives. So what recall is trying to do is, so in your precision, it's actually, you're trying to find your predicted positive versus your actual positive, your predicted positive versus your total positive, right? Your recall again is your actual positives. So when you have false negatives, you essentially have those that were, how do I put this? Because it's getting quite confusing for myself as well. So you want true positives and you don't want false negatives, and false negatives need to go into true negatives, right? Right. So you have those values that were predicted as a positive but shouldn't have been a positive, right? So you're trying to find the actual positives versus all the possible positives that were predicted. So with that, again, I thought this would have been a good metric, but this really isn't. What I'm going to do is I'm going to import accuracy score. I do a tab to show sklearn.metrics import. So it seems like from when the last time I did this, classification report already had an accuracy score, but looks like it does not now. So sklearn.metrics. So I'm just gonna do what any data scientist does, right? Accuracy of confusion matrix.
It's accuracy underscore score.
That's what I thought, but it just did not tab. Like it just did not autocomplete. Oh, that's why. Awesome. So with that, I will put in my predictions. This is my actual values. And it gives me an accuracy of 79.8, so around 80%. So it's getting almost 80% just right, which I think is pretty good. So what I'm going to do now is I'm going to predict my test.csv values. Before that, just want to make sure I clean my testing. Yes, I did. Never mind. So now that I have a model and now that I have all the coefficients trained with xtrain, I'm going to use it to predict my test.csv, because this is the file that my Kaggle competition wants, and it wants me to specifically upload, right? So that they can tell me what my accuracy score is. So to do that, I will simply have test predictions is log model predict. Yes, test. And before that, make sure test is what it is. All right, fantastic. So log model I get test predictions. Once I do that, I'm just want to see how it looks, right? All right, so it's a NumPy array, just as I thought. It returned an entire NumPy array. I want it to be a data frame, so I'm just going to do a test underscore id is actually a pandas data frame. All right, so the reason I'm converting it into a data frame is because when you go to your Titanic submission, and in the rules, I don't think I can see it here at the moment, and I was supposed to find this a lot earlier. But it has specifications on how you need to submit your test data set to Kaggle, right? Because there is an automated compiler in their side, and they really want to know whether you actually got your ones and zeros perfectly fine in correspondence to what they have. And the only way to do that is by actually connecting your passenger ID with your survived column. And then their automated compiler reads the passenger ID in that specific survived column and gives you the accuracy whether your model has done right or not. So what I'm going to do is I'm going to convert this into a data frame, right? And once I do that, if I just go ahead, it should act like a data frame, which it is. The column name is just 0, which we will change in a bit, but it has all values from 0 to 1. All values as in whether the passenger survived or not. Now, all I need to do is add the passenger ID. So to do that, I'm going to call this my submission variable. I'm going to concatenate my test passenger ID and I'm going to concatenate my test predictions. Oh, missed that. Access equals 1. Oh, seems like I got the word wrong. Oh, yes. I forgot. So we dropped the passenger ID because it was pretty useless, but now it seems to be useful, right? And so what we could do again is just, I'm going to say test2 p.readscsv. I'm going to get the entire thing again. Test.csv. Then test2.head to make sure it is what it is. And with that, passenger ID. Awesome. So I'm going to do test2. Then if I just submission or head, fantastic. It's giving me my passenger ID and it's giving me this survived column. So all I can do is mission.columns passenger ID and survived. So if I do a submissions.head again, submission.head, I have the 2 columns. Fantastic. Now, my last step for coding is just converting it to CSV, and I'm calling it submission.csv index equals false because I don't want this index over here. I just want these 2 columns, which are absolutely fine. Once I do that, let's see, I should have a submission.csv, which is right here. Awesome. So now that that's done, I just go back to my Kaggle. I want to submit a prediction. Step 1 is submitted. So I'm just going to take this here, submitting, and this is for my reference. So I'm going to say ML workshop 4 submission. Then I'm going to make submission. Unexpected column. Oh, now these were the rules I was talking about. So they want passenger ID, but I misspelled passenger ID like I usually do. And so I'm going to run this again, and my submission.csv, run that again. Once I do that, I'm going to submit once again. And take this file. And now what for? Fingers crossed. Oh man. Oh, yeah. Fingers crossed, hopefully this works. Please give me an accuracy. Alright, seems like okay, so fantastic. I got an accuracy of 75.5%. And on the leaderboard of this sort of okay or average accuracy, I'm probably somewhere around 15,000 if I remember the last time. Oh, there I am. So 15,900 and something. So I've done better than 70%, which is great. But this is essentially the entire life cycle of the data scientist. Congratulations, guys. So you've got your data from Kaggle, and like I said, Kaggle is a really good place to be, especially if you want to pursue data science. After that, you take your data, you clean it up, process all the null values, do some feature engineering, play with your data a bit, visualize it, really understand your data. It's really important to have the domain knowledge behind it. Maybe if we had the names and we had some domain knowledge, we could really understand who is there and what is a good predictor of how it survived. And then we do, the thingamajig, which is train it into a model, test it, and submit our predictions back to have this awesome score. With that, I think that was most of it.